In the meantime, last time we were talking about the CYK algorithm. How was that going? What? Okay, I guess the forced restart got rid of any animations that were on this, so we'll deal without animations for the moment. That's probably actually good for our time. Anyway, we were in the process of building up this table of answers where we were eventually going to find our answer using CYK. So let's see if we can do that. If I look combined between this slide and the next slide, it looks like the best place for this table is nowhere. All right, I'll do it here so that we can look up the answers as we go. All right, so we have some row of 5 things. We have some row of 4 things, of 3 things, of 2 things, and eventually we'll get a single answer out here that we'll see. So I want to first label this just a little bit better because I think there may have been a little bit of confusion over my scheme here. So here we have a 2D jagged array that's going to have our answers. We've been talking about this, how to fill out this table with n1 something, 2 something, etc. What does that look like? This is the cell for n11. This is n12, n13, n14, n1. No, it's 2. Monday for me too. All right. Hopefully this is at least somewhat visible. It does not look like it is remotely. I apologize. So we have n11, 2, 2, 3, 3, 4, 4, and 5, 5, which were our first things that we answered on the last slide. We determined that these were the productions. It's going to break this for a second. The productions that could produce each one of those letters of the string AA, BBB directly. So A was producible directly from the non-terminal A, B was producible directly from the non-terminal B, which allows us to fill in this is the set A, the set A, the set B, set B, and the set B. Questions on how to get the first one? The first row answered. Any production that can directly produce the substring that is just that character in the string. So we had AA, B, B, B. This is the list of non-terminals that can directly produce the substring from index 1 up to and including index 1. Index 2 up to and including index 2. Index 3 up to and including index 3. Etc. And it's starting to get a little bit harder as we start filling in the rest. So the second row, n12, needs to produce substring index 1 up to and including index 2. If we look back at our string A, B, 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 this is the substring AA. So we need some series of productions. We call it CD, such that C produces from the beginning up to some middle point, and D produces from some middle point up to the end of this substring. When the substring is length 2, there's only one place where that midpoint can be. which is right in the middle. So C needs to produce A and D needs to produce A. So knowing this, we can go back and now say, all right, what produces just A? That was A here. The A production can produce just A. So this C needs to be A, and this D also needs to be A. So now we need to refer back to our grammar to see if we have any possible right-hand side that can produce AA. Is there any such place that can produce AA? No, there is no such way to do this. So N12 is the empty set. There is no such production that can produce a left-hand side and a right-hand side that can make this two-character sequence AA. That's not to say now that this entire thing is not possible. It's just one of, it creates some constraints. If we're going to produce this, we can't have a first half just produce the first two characters in the sequence. We can't have a midpoint right here because we have no way to generate the first half of that. That's what this tells us. And we'll propagate this forward as we start answering more questions. All right, so we're going to undo all of this. And now we're going to ask the question N23, which is index 2 up to index 3. So now we need C to be able to generate lowercase a and D to be able to generate lowercase b. If we look back at our grammar, it was non-terminal production capital A that can produce the lowercase a and non-terminal capital B that can produce the lowercase b. So we're looking for any production that can produce capital A, capital B. And we see that the non-terminals S and B can both produce capital A, capital B on the right-hand side. So that tells us we have two options for producing this particular substrate. It can either come from S or B. How about 3, 4? Somebody walk me through this. Yeah.
So you're gonna look at load N33 and N44, because those are kind of like right underneath and to the side of it.
Yeah, so we can, that's another way that I haven't really talked about for figuring this out yet. You can, when you're trying to figure out where is this, it's actually embedded in the table, which is an excellent point. So when we're looking at N34, the middle point is right here-ish, if I could draw. So we need a left-hand side that can produce B and a right-hand side that can produce B. So we can do a lookup in the table of N33 and N44. This information is already embedded in the table for us. We don't have to look back ourselves at the grammar. So how do we proceed?
Then you're gonna look at any of the productions that make the non-terminals B and B.
Yeah. We're kind of going to combine this together such that we now can look at either B, we need the left-hand side to produce B and the right-hand side to produce B. So this tells us we're looking for any left-hand side that can produce BB, the combination of this and this. So we look back at our grammar and we see that the non-terminal production A can produce a right-hand side of capital B, capital B.
And then so then the set that it makes is A. This. And then the same would be on this because it's similar.
Yeah, it's exactly the same, right? If we look at the string, we're looking at a substring that contains exactly the same set of characters. So this BB is the same as this BB, even though they're offset. So here we're looking at here and here constructing our BB. And we look back at the table, at the grammar, and we see that still only the production A can give that to us. Great. Now it gets a little harder. As we continue to go up this table, we're gonna end up with more and more possible midpoints. We need to consider all of them because we are going to be taking a union of them. If there exists any way of producing this substring, we need to know all of them. Because it might be the way that produces 1,5 when we get there. We cannot stop early. So for N13, this is now this substring AAB. We have a couple options of the way that we can split up AAB. We have kind of a left-hand side and a right-hand side. We have two different ways. The left-hand side can either be A or AA, and the right-hand side can either be AB or B. And this produces AAB in some particular midpoint. Here, the midpoint is between the A's, and here the midpoint is between the last A and the B. So we're going to kind of consider all of the ways that this midpoint could produce the associated stuff. So what is this A? This A comes from here. Where is the lookup in the table? N11, right? Because we're talking about the substring from position 1 up to and including position 1. That gets us this A. So that answer is going to be right here. So we're going to combine the set that contains A with, now we need a right-hand side of AB. Where is that in the table? N23, which is right here. So we're going to combine this with the set SB. So now we need to take an element from here and an element from here to be able to produce any possible right-hand sides we are looking for. So these options are either AS or AB. Either one of these will be able to produce N13. If we can find them on the right-hand side of a production. Any place where we see AS or AB?
S and B have AB.
Yes, productions S and B both have AB. So this tells us what lives inside of N13. It's the set S and B. This is only the first half of this. So we need to go back to this and see if there's any other way that we can produce this. If there is, we need to add that to this set. So we're not necessarily done. I probably shouldn't have written it there like it's finalized yet. But we have AA and we have B. AA represents which cell that we've already calculated? N12. That's the empty set. The empty set combined with anything is going to be the empty set, right? If you have a left-hand side and you need to pick one of both the left-hand side and the right-hand side, and the left-hand side is the empty set, there's no possible pairing that we can come up with. So the whole thing's just going to be the empty set. So this is actually our entire answer. Did that logic, it was kind of quick, did that logic make sense? We need a left-hand side and a right-hand side. We combine this A with one of these on the right-hand side. If the left-hand side is empty, there's nothing there, then there's nothing that we can produce here. So that's why this is an important thing to carry forward. It can help you shorthand future work. Excellent. So that was for 1-3. What about 2-4? We are now going to be looking at this substring that we could break up into A and BB, or AB and B. Where are we going to find this? This A refers to what? Two, it's this A, right? It's in position 2 in the string. So we want to refer to position 2 in the table. All right, what is the right-hand side? BB. Where is that in this table?
3, 4.
Yeah, from position 3 up to and including position 4. So we need an element from each of these sets. This can only produce AA. We look back at our grammar. Where did that come from? Do we remember? What can produce AA in our grammar? Nothing. It's the empty set. Great. We'll see if the second half produces anything. I still want the second half here. I want A, B, and B. So AB comes from where? All right, we have a left-hand side of S and B. What's the right-hand side? Four, four, which is the set B. This can produce either SB or BB. Looking back at our grammar, where can we find either SB or BB on the right-hand side of a production? Okay. A. So between the two of these, the only thing, the first one was the empty set. The second half was just the set containing A. So when we union those together, we get the set that contains A. All right, 3, 5. I know this is truly thrilling work to go through all the way. We can either have B and BB or BB and B. This is fun. So what are the representations? This B is 3, 3. So this contains the set that contains B. What can produce BB? This is between 4 and up to and including 5. So we have B and A. So this gives us BA. Anywhere we see a BA? Nope. That's the empty set. All right, BB. This is 3, 4. And this B is 5, 5. Where do we see AB? S and B. Excellent. What changes when we move up to this row? What about this process changes?
4 butters or 4 tones rather. And
Yeah,
we can have multiple midpoints instead of just 2. We can have.
yeah, we're gonna have one more of these. Yep. So we're gonna be looking at the substring 1 to 4, which is AABB. We can have 3 possible breaking points now. We could have A followed by ABB. We could have AA followed by BB, or we could have AAB followed by B. 3 possibilities. All right, what produces all of these? We need to union all the possibilities together. So let's start right here. Left-hand side A, where is that? This A represents what in the string? Remember that this plus this is this substring. So if we're looking at just the left-hand side of AABB, and the left-hand side is A, that represents this A, the first A in the string. So what substring represents that? 1, 1. What's right here? So this left-hand side is going to be the set that contains A. The right-hand side is ABB. Where is that located? 2, 4. Hear that, right? It's from index 2 up to and including index 4. I look up to 2, 4 in the table gives us the set that contains A. The only possibility of combining the left-hand side and the right-hand side gives us AA. We look back at the grammar, what can produce AA? Nothing. Dead end from this one. Maybe I should be writing this up here. Dead end for this one. All right, breaking this in half this way. We have AA and BB. This AA comes from where? 1, 2. That's the empty set. We don't even need to go further. This is going to be the empty set. AAB, where does that come from? 1, 3. That is S and B. And the right-hand side, 4, 4. So this can produce either SB or BB. Looking back at our grammar, what can produce either of those? SB or BB? Just A. Now we've calculated all of these, we union the empty set and the set that contains A all together, we get the set that contains A, which is what gets written here. 2, 5. We're almost done. Possible places we can break this: A, B, 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 A, B, 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 or A, B, B, and B. Where are the associated lookups? This A is now 2, 2, not 1, 1. So we have a left-hand side of A and a right-hand side of B, B, B. Where is that located? 3, 4, 5. Produce AS or AB. AB and BB. AB is what? 2, 3. Left-hand side of SB. A right-hand side of 4, 5. So this can produce SA or BA. Looking at the last one. ABB. That is 2 up to 4. So left-hand side is A. Right-hand side is just this last B, which is 5, 5. So this can produce just AB. So now we're looking for any productions that can produce any of these outcomes. AS or AB or SA or BA or AB. There's no BB here, so the answer is still just S and B, because they can produce the AB that we're looking for right here.
Quick question.
Yeah,
We consider order as well when we're looking at that. That's why we
Yes.
don't like consider BA as AB.
yes, the left-hand side has to come first, the right-hand side has to come second.
Okay.
So order does matter between the left-hand side of this and the right-hand side of this. All right, one last question, N15. We finally filled out this table to be able to answer this. We don't know where we're going to need to look. In fact, we need to look all over this table as we come up with this, which is why it's so important that we have this table filled out. All right, we're looking at the whole substring, which means that there are 4 places we could break this. We could do A and A, B, B, B. We could do A, B, sorry, A, and B, B, B. We could do A, B, and B, B. And we could do A, B, B, and B. Okay. All of these things, where could they come from? We have 1, 1 and 2, 5 We have 1, 2, and 3, 5. We have 1, 3, and 4, 5, and we have 1, 4, and 5, 5. So these are the important cells to look up, right? Once we know this, we can just quickly do what is the substring, go find the appropriate place in the table. All right, 1, 1 is our left-hand side of A. 2, 5 is our right-hand side of SB. Gives us AS or AB. 1, 2, and 3, 5. Left-hand side is the empty set, so we know this is going to be the empty set. We don't even need to consider it. AAB is 1, 3, which is SB. Three, 5. No, 4, 5. 4, 5 is right there with an A. Gives us SA and BA. Last one. 1, 4, and 5, 5. 1, 4, left-hand side is A. And the right-hand side, 5, 5, is B. Which again gives us AB, which we already have, but just in case we didn't have it, we still need to check. So all of the things that can produce any of AS, AB, SA, or BA back here. It's again S and B, right? So we're going to put S and B as our final right here. And so the very final question that we ask is, does this set contain S? If it does, it's in the language. If it does not, it is not in the language. Does that make sense as to why? That S start symbol, what we've determined is that it is possible to produce this string AABBB from the start symbol. Using the start symbol, we can break this down in some capacity to be able to tell us the productions that we need in order to do this. What are those productions? We haven't really stored that, but we've been able to answer the question, yes or no, this grammar can produce this string. A lot of work to be able to do so, but let's actually analyze that time complexity. Because this is kind of an important thing. We talked about brute force being exponential. What is the time complexity of filling out this entire thing? We talked about the part of it that was filling out this, right? We determined that it was quadratic to be able to fill out this table. But how expensive is it for us to be able to fill in one of these things in the worst case? How much do we need to parse? Which box was the hardest one for us to fill in? Last one. It involved the most work, right? We had to break this down into 4 things and answer 4 sub-questions. Do we agree that every single box is less work than that? It may be the same order, but this is at least the bound of how much work you will have to do. So it's going to be less work overall than propagating this much work to this many things. How much was this if we had to do this in terms of how many things did we have to do? How many sub-questions were there? There were we broke it into pieces and then we had to answer, there were 8 lookups, right? But it's 4 times 2 lookups and the 4 is n-1. So this doubling it is not super important in the same order, but it's always going to be the length of the string -1, telling you that this is a linear time process in the worst case. Here it's going to be a constant time process, but it's slowly going to build up to being a linear time process by the time we get to here. So if you average linear, 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 and the last row is constant, or as it gets closer and closer to constant, you'll end up with linear as your average complexity. So if we take a quadratic sized table and we ask a linear time question in the worst case for each one of those cells, what order do we end up in? We're analyzing this code. I'm just taking what we just talked about and put it into kind of code context. Pseudocode context. And sorry, this should be squared. For each of the length of W squared cells, we determined this was quadratic. We're going to ask a number of questions that's based on the length of the string.
Thank you.
Yep, whenever we have something inside of a loop, we multiply. So we basically have something that looks like length of W squared, length of W, which is in the order big O. We know it's big O because all of these were worst case assumptions. So big O of the length of W cubed. This gives us a cubic function. What is better, exponential or cubic? Cubic, significantly. So this is actually better than cubic, but we have a worst case bound on it of cubic, which is very nice. We've gone from something that's impossible to something that is possible for most strings we're going to care about, which is incredibly useful, which is why this algorithm is used. So yes, this is going to be your first project of the quarter, or the first project option of the quarter. Remember, you only have to do one project, but if you'd like to get this out of the way, which I would recommend, less crunch at the end of the quarter, then all you're going to need to do is implement this. I'll have an official write-up out in the next couple of days, but basically you're going to be reading from a text file some number that is the number of grammars and questions to follow. Then you will read in that many grammars, and then there will be another number telling you the number of query strings that are following about that grammar. You will read in that many strings and generate yes and no for that many strings. And then you'll do that for each grammar, and then you'll output all of that back to another file. And that should be easy enough. Pretty straightforward. The hard part is going to be the implementation. And as usual, I will say you cannot use outside libraries. Everything that you use has to be coded yourself. I see questions like, why?
Programming language of our choice.
That's a good question. That will depend on grading. Basically, yeah, it's pretty, everyone should have some kind of Python setup for sure.
Python, Java too.
Yeah, yeah. So I would say either Python or Java. I think that's perfectly fine. If you want to do it in some other language, talk to me and I can talk to Harley, or you can reach out to Harley directly saying, how hard is it to set this up? And make sure that at that point, part of the assignment would be communicating your runtime environment. Basically, if he can't reproduce and run your code, that is bad. Questions on this process?
I just have one little slide. It says because N15 is not the NP set, he said.
Yeah, actually, you're right. I actually corrected this, but this is an older version of these slides. So yeah, it's not the empty set. It needs to, because N15 contains
Okay, so it needs to contain this.
Yeah.
Like, even if it just contained immediately for the.
Right, that would say, we need to be able to get from the start state to that place to be able to do it. Which was why we need that start symbol, so thank you, that is an excellent point, there is an error on the slide. This is said, it should say because N15 contains the start symbol, not because it's not empty. Because yeah. Excellent point. Other questions? Is the process at least somewhat clear? There will be future homework. To have you go through the process, it won't be any bigger than this. This is as big of a table as I can reasonably ask you to do by hand. This is why we write algorithms to do this for us, because, I mean, even this took an hour, almost an hour, half an hour, to set up and fill out, explaining each step of the way. It's kind of a pain. Why we make a computer do it? All right, last 10 minutes of class, I really want to start diving into pushdown automata. So everyone have everything they need from the board?
I have one quick last question about
Yeah.
when you assign them, is it gonna be like, we have multiple options, but like, there's like a window to do them?
No, by the end of the quarter.
Okay, cool.
So you can put this off to the end of the quarter if you would like full information about all of the possible projects. If you implement multiple projects, I may be willing to dole out some extra credit. So I see almost no reason you shouldn't at least give this a go if you have some time. That's basically the idea. The projects are the kinds of outcomes from classes that you're going to be able to include in a code portfolio to be able to give to potential employers. So I want to make sure that you have opportunities in every class to produce something for your code portfolio. This would be an excellent way to say, if they say, what is dynamic programming? Or do you have anything that shows understanding of dynamic programming? This would be a great place to go, because it's not just a dummy toy problem. It's something that's actually solving something that is related to a significant computer science component, which is compilers. So a compiler would implement an algorithm like this for the membership question. Of a context-free grammar in Chomsky norm. Okay, let's hope we have some animations for this next set. All right, so we're shifting one more time away from grammars for a while, thankfully, probably sick of them by now. And we're going back to the world of state machines and automata. Yay! Want subtitles, go away. All right. That was wonderful. We all need, yeah. So just like with regular languages, we have lots of ways to represent context-free languages. We've talked about grammars as a way to do so, but we need some kind of state machine. All right, refresher, difference between a regular language and a context-free language.
Regular languages have to be right or left, linear.
Right or left linear within grammar forms, yes. Correct, so that's the difference in grammars.
Right.
What else? What other, if we were to abstract it into the biggest form, what was the biggest difference between these two language classes? It had to do with memory. Or what we need to remember as we're parsing a string.
We use the analogy that for a context-free grammar, you might need 2 stacks as opposed to just 1.
You actually do only need one, but you didn't need any with a regular language, right? You just straight up, it didn't matter where you were in the string, you were in a particular state. And if you were in that state, all times you were in that state were equivalent with regards to what you could produce going forward. If you were in some state in a DFA or an NFA, there was no context to being in that state. It didn't matter why you were in that state. If you were in that state and then you found yourself in that state again, so at some point later in time, your options are precisely the same. Because of that, you don't need additional memory storage to give context to why am I here, which you might ask yourself every Monday when you first wake up. So with context-free languages, we do need that memory because just because you're in a particular state doesn't mean that you're not in that state for a different reason. And you can think of this as like doing a peek to the top of the stack. What is the top of the stack character? If the top of the stack character is different, the options that you have may be different, even within the same state. That's going to be the easiest way to understand how we're going to talk about pushdown automata. So a state, what are you doing? A state is a combination now of the state that you're in and what symbol is on the top of the stack. So we need additional memory in the control unit for a state machine. Here's a question. Is there a limit to the amount of memory needed to be able to accept or reject a context-free language? Do we place any restrictions on things like the number of productions in a grammar? Or the number of times you can visit a particular production within a grammar? Or anything else of the sort? We have infinite strings of arbitrary lengths. So we cannot limit the amount of storage we have for a stack. We want to be able to accept, if we're looking at the language A to the N, B to the N, we want to be able to accept the string that is a quadrillion A's followed by a quadrillion B's. Do we have enough memory for that? We don't ask the question. This is not a physical constraint or a digital constraint that we place upon recognizing language. That is a constraint that is based on an individual machine that we have. So here's the difference between what is practical on a machine that we can run today and what is theoretically possible given a machine with infinite storage. So we are more so asking the question, what is theoretically possible on a machine with infinite storage, rather than what can we run on our machines today? We'll talk about that distinction in a lot more detail when we start talking about the limits of computation. It turns out to be a very important practical question, but it's also important to understand what is theoretically possible to be able to answer questions like, is it worthwhile to continue to shove more transistors into a board? Yes or no? Is it actually worth going through that process? What will it unlock with our ability to do computation? So we'll still use the example A to the N, B to the N. We know it's not regular. Is there a maximum number of A's that can come before the B's? Practically, yes. Theoretically, no. Because we have limits to memory in our machines, there is theoretically an upper bound if we were to implement this ourselves, and that is bounded by either RAM or hard disk space if we're going to use page files. So in the worst case, how much memory do we need? Infinite. So what is a pushdown automata? It's going to look exactly like an NFA, except that we're dragging along an infinite stack with us to every state. Think of it like a bag of holding from Dungeons and Dragons, or something of the sort, where there's just, it opens up and there's this infinite storage space where you can shove in whatever you want and there's no limit, except you know the last thing you put in and it's ordered so that you can pull it back out. We do need to define the stack alphabet and what we're going to call the stack start symbol, because we need to be able to determine when the stack is empty. Think of this like in your own implementation, the isEmpty method that you would call that would return true or false, the stack is empty or not. In a pushdown automata, there's going to be a letter or something that will signify that the stack is empty. So when we do a peek, we can see that, yes, the stack is empty. We usually use lowercase c for that stack empty symbol. So again, we have a very similar looking image. We're reading from an input where each one of these will be a character and a string. We have a control unit. It's going to be a representation of some number of states, just like before. We're going to have initial states. We're going to have final states. We're going to have transitions that take characters or may not, because it's non-deterministic. We can have lambda transitions. But we also have to define what happens to the stack on each one of those transitions. Because of this, there may be multiple transitions from a state to itself or to other states, all consuming the same input character, depending on what's on the top of the stack. If the top of the stack is an A, go here. If the top of the stack is B, go here and consume an A, etc. So here it is in all of its glory. It's not as scary as it looks. It's basically just what I've said. We have a finite number of internal states. This is just the states, Q0, Q1, Q2, etc. We have the input alphabet, just like we did before. But now we differentiate between the stack alphabet and the input alphabet. The stack is going to have its own language representation, which may be a perfect mirror of the input language. Something like, when you see an A, push an A onto the stack. When you see a B, pop an A off of the stack. Wouldn't that be a great way of reading A to the N, B to the M? You read A's until you read your first B. For each of those, you push an A onto the stack. Transition on your first B, and now you pop A's off of the stack every time you see a B. You reject if you see an A again, and you reject if by the time you're done seeing B's, the stack is not empty. If the stack is empty, you can lambda transition to a final state. We'll talk about this in much more detail tomorrow, but I can answer any questions people have in the meantime. Yeah.
What's the name for the upside down L?
Yeah. This, I believe, is row.
Row?
What happens? This game job.
Is it? Yeah. Is it what's a gamma?
There's an uppercase.
Oh, yeah, uppercase. Yeah, there we go.
It's gonna be brand fun.
Even my read expresses. So again, we'll talk about this more, but. Good stuff.
So, John.
It doesn't respond well to
I really don't know.